Hi, my name is Jörg Oberdörfer. I'm working as a probe lab manager here at GE Sensing and Inspection Technologies in Hürth. Today we want to talk a little bit about the DGS method. DGS stands for distance gain size and is a method to compare real discontinuities with flat bottom holes at the same location, giving the same echo amplitude. Since DGS bases on a printed diagram, which is valid for each probe of one type, you do not need to have all the different test blocks anymore containing all the different flaws, but can use this diagram to really do the job. Today we want to do a tutorial about DGS, showing you a hands-on how you do a DGS measurement. We also want to introduce to you the trueDGS technology, a new technology that was developed here at GE Sensing and Inspection Technologies, and which is not only applicable to conventional probes, but also to phased array probes.
Within the DGS diagram, the distance dependency of the echo amplitudes from large reflectors, in this case the back wall, and small reflectors, flat bottom holes having different diameters, is shown graphically. When using the DGS method, the term equivalent reflector size, or ERS, is used when referring to the diameters of flat bottom holes. For example, a real discontinuity might be stated to have an equivalent reflector size equal to a 3 mm diameter flat bottom hole. The DGS diagram therefore exactly describes the distance laws, which depend solely on the shape of the sound beam and the reflectors. Additionally, the noise level is also shown on the DGS diagram. This noise level tells the user the difference in dB between the echo amplitude of a given ERS and the noise level at this specific depth. As described, the determination of the equivalent reflector size is based on the comparison of two echo amplitudes. The echo from an unknown reflector is compared with the echo from a known one or a reference reflector. In practice, different types of reflectors can be used as reference reflectors. When testing using normal beam and TR probes, a flat back wall is often used, which is struck perpendicularly by the sound wave. This can either be the back wall of the workpiece itself or the back wall of a reference block. As an example, let us assume that the back wall of our workpiece is 200 mm in depth and produces an indication on our ultrasonic floor detector, which needs an instrument gain of 32 dB to be brought to 80% screen height. The back wall curve is marked at a depth of 200 mm, and we keep the gain of 32 dB in mind. Let us next assume that we want to judge a discontinuity that produces a signal on the screen at a depth of 100 mm, which needs 53 dB of instrument gain to be brought to 80% screen height. Please be aware that both signals have to be brought up to the same screen height, regardless if it is 80% or a different value. The gain difference between the reference echo and the echo from the discontinuity is 32 dB minus 53 dB, which equals negative 21 dB. Starting at our back wall reference point on the diagram, we must move down 21 dB and then across to a depth of 100 mm, since this is the depth that we measured on our discontinuity echo. On the diagram, the final position found in this manner allows us to determine the diameter of the equivalent reflector size. In this example, the final position rests on the 3 mm equivalent reflector size curve, indicating that the discontinuity has the equivalent reflectance of a 3 mm diameter flat bottom hole. When angle beam probes are used with the DGS method, normally there are no back walls available that are oriented perpendicularly to the sound beam. For this reason, one frequently uses the cylindrical surfaces of the standard reference blocks V1 and V2. Correction factors specific to each probe type are supplied on each DGS diagram that correct the differences between the signal from the cylindrical surface and the reference signal from a flat back wall at the same depth. The symbol VK, shown on the DGS diagram, is the amplitude correction value, which shows the number of decibels that the echo from the cylindrical surface of the reference blocks is larger than when having a positive dB value, or is smaller than when having a negative dB value, the echo from a flat back wall at the same distance. The subscript K1 is used for the V1 reference block, which has a radius of 100 mm. The subscript K2 is used for the V2 reference block, which has a radius of 25 mm. In the example shown here, if a gain of 30 dB is needed to bring the echo from the cylindrical surface of a V1 at 100 mm depth to 80% screen height, then one would need an additional 10 dB of gain to bring the echo from a flat back wall at 100 mm depth to 80% screen height. After making this correction, a DGS evaluation can be performed just as described previously using normal beam or TR probes. One last comment regarding sound attenuation. On each of GE Sensing and Inspection Technologies' DGS diagrams, the remark alpha equals 0 dB per meter can be found. This means that the given diagram is only valid for attenuation-free test materials. Since this is an ideal assumption, the user is obliged to know the specific sound attenuation of the material they are testing, and must correct all echo amplitudes if their material attenuation is not negligibly small. We'll help you get it right.